Hi, everyone, and thanks for listening in on another Building IQ 10 on the 10th Tech Podcast, where a range of artificial intelligence, machine learning, and data science topics are explored in 10-minute episodes each 10th of the month. Today, we have the pleasure of speaking again with Building IQ's senior data scientist, Dr. Rami Khushaba. Rami has computer and electronics engineering degrees, as well as a PhD in biomedical engineering. Rami has worked in fields including sleep apnea breathing disorder detection using machine learning. Rami, happy to have you with us on this episode.
Thank you, Christine. Thanks for having me. And thank you for allowing me to talk more about this Epiphany engine.
In a previous episode with you, Rami, we talked about Building IQ's Epiphany inference engine, and we dove into one of the particular tools named the influence map. Can you give our listeners a refresher on the Epiphany engine overall?
So Epiphany is an inference engine that employs artificial intelligence to uncover how the data is interconnected, dependent, and influenced within a system. So basically think of this as if you have like a bunch of assets in a building or in any kind of like systems, you have few components. These components are sending data through IoT connections, and you want to know by looking at the data which asset is influencing which other asset. Which asset is also influencing, let's say, the overall performance of the system as one unit, and the, let's say, power consumption as well. Who's using, or which one is using more power? So to answer questions like these, we have used machine learning and artificial intelligence algorithms. So Epiphany, like by using Epiphany, it will allow you or give you the ability to distinguish also your offering from other offerings from competitors, because we look mainly at data to identify what's happening, what's going on like right now. So let's say the available systems in the market or in the literature, let's say, they all somehow rely on a set of rules. But what if your system has a problem? It's not really following the rules. What can the rules do for you? So this is where we come in. We say, okay, we don't only rely on rules, like we can have a look at the rules, but what we do is get the data, see what's actually happening right now. And that's where Epiphany comes in very powerful.
Thanks for that overview. Rami, talk more specifically about the tool sets that fall under the Epiphany engine.
Okay, the main parts of Epiphany, as we spoke previously, were the three components: the influence maps, the influence delta maps, and the correlation map. We spoke previously about the influence maps, where it allows you to have a look at the, let's say, influence of a component on a reference point. Let me put that way, like in a simpler way. Imagine you have a huge commercial building and you have, like, let's say, assets, different assets, and you want to know which of these assets is consuming more power, which of these assets is changing the amount, or let's say the amount of kilowatts it's using from day to day, and why. And these are the answers we help you to answer. So again, with the influence, if you use the influence heat maps, you can use the power as a reference point, and you try to say, okay, what is the impact of all the assets on the power, and show me that. And then you can say, how is that different from yesterday or the previous week or previous month or even years if you want to go back in data. So that's where the delta comes in. But then, okay, if you know that something has changed on influence on power, it's using more power, it wasn't doing that previously, then the third question is it why? Why is it doing it today? Why it hasn't been doing this like for the last few weeks, or let's say days, weeks, or months? Why is it suddenly doing this today? This is where the correlation map will come in, which is the third tool. So again, we spoke about influence and delta in the previous episode, but this time we're going to focus on the correlation map, which is showing the relationship, or let's say the direction and strength of conditional correlation among data points. And that's why we call it the correlation map.
Great. Let's focus more on the correlation map. Take us behind the scenes a bit on the idea behind this tool for buildings.
With the correlation map, we don't use like simple measures available in the literature, like the, let's say, canonical correlation stuff like Pearson correlation coefficient, or even mutual information. Like we rely on these. We had our basic analysis based on these, but then we evolved into measures of causality. So let me give you a brief like idea about what's going on over there. With the Pearson correlation, it tells you about the linear relationship between the different time series that you are looking at. It tells you, are they like increasing or decreasing together in a linear fashion? So that's not obviously enough for our case. So then you would evolve into more advanced like measures of, let's say, correlation and dependency, and you can start looking at something like the mutual information. Mutual information can give you some sort of information about the nonlinear relationship between the two time series or two assets that you're looking at. But then again, it only tells you that there is a relationship, but it doesn't tell you, is this relationship between X and Y, like, is it because X is affecting Y or Y is affecting X? So the direction of information flow, that was the missing part. And then we started digging into more measures of like kind of relationship between time series. We tried so many of them from the literature. We've been doing our research. Eventually we end up with causality measures. So with the causal impact estimation measures, we ended up using one of the, let's say, measures that we have developed further. It's also based on information theory to tell us about the information, the direction of information flow. So in this way, I not only tell you that there is a relationship between asset X and asset Y, but I also tell you who's impacting who by more. Like, is X impacting Y more than that? Like, Y is impacting X? And what's going on, where is this coming from? So I can even track it. I can go into like the previous layers of connections between these assets, not only at like one layer, but I can go into different layers of relationships.
Rami, can you give our listeners an example in a practical way to help us understand how this tool works?
Practically, you can, to understand like the concept of causality, let me give you two examples. One of them from the building side or smart building side, and one of them is just a general example. On the building side, you, for example, you see, let's say the boiler enable is oscillating. Boiler enable is going on, off, on, off, on, off all the time, and you want to know what is causing that. So you use our tool, the correlation map, and you like run the tool on a specific period of time, for example, 2 to 3 days where the boiler is oscillating. And then you start getting all the points that influence or have some sort of causal impact or causal influence on the boiler enable. And then you can see, for example, the hot water valve and the hot deck set point, they are being oscillating. And you can find more points, and you can start tracking the mechanical relationships. And then if you have some knowledge about the mechanics of the building, you can start relate these, let's say, points to the actual boiler, and then you understand why it was causing, like why the boiler was oscillating. And eventually in this example, we found at the time it was the PID loop because it wasn't tuned properly. So you had some oscillation over there. So if you are not in this field of research or of work, you wouldn't really like get much from this example. So let me jump to the other example. It's a very famous example which is available on the internet, which is the per capita consumption of margarine in one of the US states. And the example showed like two curves. One of them was for the divorce rate in Maine, and the other one was the margarine consumed in the same state. And you would see that both these curves were like, let's say, exactly correlated with each other. The correlation could be like 0.9 or 9 or something, which means very high correlation. So the less margarine they consumed, the, let's say, the more less divorce happened, and so on. So the curves go together, like they increase together and decrease together at the same time. So can you say that the consumption of margarine then has a causal impact on divorce? So if you eat or don't eat butter, let's say, you get to divorce or not. That's not really, let's say, a causal impact. So you have to differentiate between two things having the same pattern or following the same pattern, and from one element or one thing having like a causal impact on the other. So the impact of margarine on the divorce is not really causal. They just happen, the curves just happen to be looking similar, but of course there are other factors affecting both of these, like let's say curves. They are not causing each other, but they are correlated with each other. And that's where we say correlation does not imply causation. So things can be correlated, typically correlated, but that does not mean they are causing each other again. So you have to run some tools of causal impact estimation to verify if there is any kind of information flow from one of them to the other.
Got it. That example was really helpful. With Epiphany Engine and the correlation map, what would you say are the main benefits for building owners and facilities teams in their daily operations?
So the main one is that you don't have to, let's say, browse or sift through hundreds or even thousands of time series data coming from the different IoT sensors. Imagine you have a building, and this happens like almost every day for us, where we had a look at a building with, let's say, average size of a couple of thousand of points. So imagine you have, let's say, a PID loop tuning again issue, which is impacting several other components, and you want to know, like, you have seen something and you want to attribute that to its root cause. But if you have 2,000 time series, how many days would you typically need to go through these, inspect them, and tell me what caused this behavior? We have seen examples with our teams where we had a much smaller building with only like 300 map points, or let's say 300 time series like available to them, and they took almost 2 to 3 days to like browse through these, look for the main cause of some problems. So imagine if that grows to 10,000 or 20,000 points. How much time do you need? We save you all that time, and we give you the result by click of a button. You click the button, the tool will analyze the whole thing for you and will give you back the most probable cause, or let's say the actual cause, actually depend on the type of a problem you're looking at. We'll list all the like potential highly ranked like causes of this problem, and we'll tell you the problem lies here. Go and check these points. So we save you the time, and we indicate or direct your focus to the right, let's say, asset or equipment in the building.
Is there anything in closing that you would like to add about the correlation map that we didn't cover already in our conversation?
Okay, so there are other causation measures in the literature. One of the very famous one is Granger causality that has been studied in economics before and many other fields. But there are also the measures that we are using based on information theory. And there are so many studies nowadays, or actually in the literature since so many years, comparing these two measures with several others. The whole idea is that these are actually causation measures. You will get some people criticizing one of these measures depending on, let's say, the research group that you have been working with. Are you more on the machine learning side? Are you more on the econometric side? Are you more on the business and marketing? So it depends where you're coming from as well. But these are like causation measures. And as I said, there are very famous measures like, for example, Granger causality, transfer entropy, and so many others. You can also use some regression models and some other techniques, but overall the methods have been verified. And what we add on top of that is that we not only look at causation measure based on that, but we are developing something more advanced actually, where we also look at the actual mechanical relationship and try to merge that with the causation estimation. So if I say, for example, asset X is influencing asset Y, I also look at the mechanical relationship. Is that making sense mechanically? Can that happen? Or that's like cannot happen? Like, is that in, let's say, zone 1, level 1, and zone 51 and level whatever? So can that mechanical relationship, like, can that happen mechanically or not? So we also verify these kind of stuff nowadays, and we are taking our research further in this direction.
Great. Rami, it was such a pleasure to have you join us for another episode to dive deeper into the Epiphany engine. To check out other BuildingIQ 10 on the 10th Tech Podcast episodes and to learn more about BuildingIQ's technology-enabled services, visit buildingiq.com. Thanks everyone for listening, and we hope you'll join us again next month on the 10th.